Hello मेरे प्यारे बच्चों and welcome back. I know, exams are just around the corner and that tension is probably building up, right? But hey, don't you worry.
Because today, we're going to smash one of the most important chapters, moving charges in magnetism. We're going to break it down, make it super simple, so that by the end of this, you'll be like, oh, that's it. You'll feel so confident you could probably teach it to your friends. So let's get right into it.
All right, let's start with a bit of a story. How did anyone even figure out that electricity and magnetism were, friends? For ages, everyone thought they were two totally separate things. But then, one scientist had a total aha moment.
And that scientist was Hans Christian Oersted. Way back in 1820, he figured something out that changed everything. The key takeaway, the main point, is this. Whenever a charge moves, or you have a current flowing, it creates a magnetic field all around it. Seriously, this one idea turned physics upside down.
And you want to know how he found this? It was such a simple experiment. He was just doing his thing, working with a wire that had current flowing through it, and he happened to notice that a compass nearby, its needles started to twitch and move. That's it. That little deflection was the very first proof that electricity could create magnetism. Such a small observation, but with absolutely huge consequences. Okay, so part one, a moving charge makes a magnetic field. Got it? But what happens when another moving charge flies into this field? Well, it feels a force. And this force follows a very, very specific set of rules. It's the rule of the game, really. And this rule has a name, the Lorentz force. Now, the full force has electric and magnetic parts, but for this chapter, our absolute hero is the magnetic force. I know that equation looks a little scary with the cross product symbol, but don't sweat it. All it really means is that the direction of the force is kind of special. It depends on both the direction the charge is moving and the direction of the magnetic field. Now, this magnetic force has some really quirky features. First thing, if the charge is just sitting still, the force is zero. Nothing. Nada. A magnetic field doesn't care about stationary charges. Second, and this is super, super important, the force is always perpendicular at a right angle to both the velocity and the field. It's like a constant push from the side. And because it's a sideways push, it can't make a particle go faster or slower. It only changes its direction. So how do we figure out the direction of this sideways force? With this beauty, the right hand rule. Bacho, pay close attention. This is a board exam favorite. Everybody, do it with me right now. Seriously. Take your right hand, point your fingers in the direction of the velocity, V. Now, curl your fingers towards the direction of the magnetic field, B. And boom, your thumb is pointing right in the direction of the force, F. Okay, let's try it out. Quick check for you. Imagine a proton moving along the positive x-axis, so to your right. The magnetic field is pointing up, along the positive y-axis. Use your right hand. Which way is the force pushing it? Did you get it? Your thumb should be pointing straight out of the screen towards you. That's the positive z-axis. And remember, this rule is for positive charges like protons. If we were talking about an electron, a negative charge, the force would be in the exact opposite direction, into the screen, along the negative z-axis. Simple, right? So, we know how magnetic fields push charges around. But how do we even calculate the strength of that magnetic field in the first place? Well, for that, we have two amazing tools in our physics toolkit. First up, we have the Biot-Savart law. The best way to think about this one is to remember Coulomb's law for electric fields. This is basically its magnetic twin. Where Coulomb's law finds the electric field from a point charge, the Biot-Savart law helps us find the magnetic field from a teeny tiny piece of a wire carrying a current.
And then we have Ampere's circular law. This one is your best friend, your shortcut. When you have situations with nice, neat symmetry, like a long, straight wire or a coil, this law makes the calculations so much easier. It basically connects the magnetic field around a closed loop to the current poking through that loop. So for your exams, here's the strategy. You gotta know when to use which tool. Biot-Savart is the universal one. It'll work for any weirdly shaped wire, but honestly, the math can get a bit hairy. Ampere's law, though, it's your go-to for symmetrical problems. It's fast, it's easy, and it's elegant. Choosing the right law will save you a ton of time and effort.
And now, for the coolest part, why do we learn all this stuff? To build amazing things, that's why. Let's see how all these ideas come together in some really important devices you see around you.
Let's start with this thing,
a solenoid. It looks complicated, but it's really just a long wire wrapped into a tight coil, like a spring. When you send a current through it, something awesome happens. Inside the coil, you get a really strong, and this is the important part, a very uniform magnetic field. It acts just like a perfect bar magnet.
And this is where Ampere's law is just brilliant. The formula to calculate that super strong, super uniform field is incredibly simple. It's just B equals mu0 times N times I, where N is just how many turns of wire you have per meter. That's it. Another must-remember formula for your exam. And this isn't just some abstract formula. Let's put some real numbers in there. If you take a solenoid from your textbook, say example 4.8, with 500 turns and 5 amps of current, you just plug those numbers in, and you get a real measurable magnetic field of about 6.28 millitesla. See? From a simple formula to a real-world value. Okay, remember how a magnetic field pushes on a current? Well, if you make that wire into a loop, the pushes on opposite sides create a twisting force, a torque. And this simple twisting idea is the heart of a super important device, the moving coil galvanometer. It's the original tool we use to measure electric current.
So how does it actually work? It's a beautiful little dance in 4 steps. 1. The current you want to measure flows into a coil. 2. The magnetic field creates a torque, which makes the coil want to rotate. 3. A tiny little spring that's attached to it pushes back, trying to untwist it. And 4. The needle stops moving when the magnetic torque and the spring torque are perfectly balanced. The more the needle moves, the more current there is.
Phew! That was a whirlwind tour, but you guys kept up brilliantly. And as a reward, here it is, the cheat sheet. All the big, important formulas from this chapter right here on one slide. Go on, take a screenshot, write it down. This is pure gold for that last-minute revision before you walk into the exam hall.
And just like that, that's the whole chapter, all wrapped up and ready for your exams. How are you feeling? A bit more confident? I really hope so. You've got this. Hey, do me a favor, let me know in the comments which chapter is giving you the most trouble, and I'll make the next explainer on that one. All the very best, mire pyare bachcho, go and rock those exams.